this evening. The numbers are increasing slowly, and as you'll mostly hear soon, from next meeting, from the August meeting, we will be only doing it in the auditorium. There will be no streaming, and we'd just like to encourage our members to come along and listen to our, and have a full auditorium to listen to our lecturers. It's also a great pleasure to welcome Professor Andrew Forbes. Sorry, we'll just wait for a second. While the technical people are just doing their thing, as I said, it's a great pleasure to welcome Professor Andrew Forbes. Now, if I was to read Andrew's CV as an introduction, we'd be here till 7 o'clock. It's got a very long and extensive CV, and so I'm just going to extract certain parts from it. Andrew, in his CV, quotes that he's found himself at various times as a teacher, a janitor, secretary, receptionist, webmaster, systems engineer, sales rep, manager, director, and sometimes scientist. So he's obviously quite a versatile fellow with quite a range of activities. He was educated at the University of Natal, Durban, where he obtained a higher diploma in education and a PhD in physics. He started his career as a teacher at Springs Boys Farm, just down the road from here. But then he moved to the Atomic Energy Corporation and various other organizations before spending 11 years at the CSR National Laser Center, where he was the chief researcher and also research group leader. In 2015, he was recruited by the then Vice Chancellor, Principal of WITS, Adam Habib, to become a distinguished professor in the School of Physics, where he formed and headed the Structural Light Laboratory. Adam Habib at that time was searching around for real talent, and he obtained two people at least from the CSR. One was Andrew, and one was the late Bob Scholes, who also came to lecture with us here, but unfortunately died accidentally. The National Research Foundation, then it was known as the NRF, designated Andrew as an A-rated researcher. This is the top, the highest level, not just internationally recognized, but internationally acclaimed. And he's received many other awards and recognitions, including the 2020 South African Institute of Physics Gold Medal, for which I believe he was the youngest ever recipient. Is that correct, Andrew? His time, this is the end of his CV, spends his time having fun with taxpayers, money, researching structured light. Well, Andrew, the buck ends here. Over to you to present.
I'm not sure how to do it. There's no way yet to switch the camera. And I want to shut this down. I'm just
All right.
see if I'll swap the
I'm
camera.
not sure if I should hold this because then I tend to wave my hands. So I can give it a try. If it doesn't work, I'll come back here. Can we please just put it on? out of air. So that's a little bit of an intriguing idea, because if you have a look at the lenses that you probably have on hand nearby, or look at the person around you, you'll see that they're always made of glass or plastic, but some solid material. Okay? And what we're going to do first is ask, how do lenses really work? And understanding the physics behind lenses, trying to see if we could change the paradigms around how to engineer them. So as Rob said, I'm based in the School of Physics. I run a lab that looks at structured light. I'm at WITS, and so I have to tell you that this year we're celebrating 100 years, the centennial. And hopefully you'll be invited to the big celebrations in September. Have you?
Yes.
Very good. If you haven't, you should gate crash anyway. They're going to have great light shows illuminating the Great Hall, telling a story about the history of WITS. And in fact, if you come a little bit to the left of the Great Hall, you can just make out the School of Physics behind it, or behind these trees. And inside the School of Physics is my lab, of course. And on this weekend, where they have all the big celebrations, we're going to have demonstrations about light and the power of light and how you can innovate with light. So do come around to that. But let's come to the topic then. And so the topic is lenses to begin with. So what do we know about lenses? If you've ever played with magnifying glasses, or you go and speak to your grandchild, they'll immediately tell you that what lenses do is they concentrate lights. So imagine I have a lens here shown in blue. It could be made of plastic or of glass, it doesn't really matter. But you see that it's sort of thicker in the middle and a little bit thinner on the edges. Not always, but the conventional lens would be like that. And what's going to happen is we're going to draw our light as these arrows. So it's like rays of light, almost like this laser beam traveling from the pointer to the board. If you imagine that I joined my hand to where it landed with an arrow, that would be the ray of light. So here we have rays of light coming into the lens, could be sunlight or from the pointer. And what does the lens do? Well, what it does is it bends the light. So the light that goes through the middle here passes straight through. You can think of it as being bent but straight. It's a little bit of an odd way to say it, but I'll explain why I said that in a second. What about the rays on the edges? Well, it turns out, and I'll explain in the next slide why, that the thickness and the angles of the curvature around the structure bends the light at just the right angle for the top ray to overlap the middle one over here, and symmetrically the bottom ray to come to the same point from the bottom. So what the lens has done is it's bent the rays in such a way, they still remain straight lines, light travels in a straight line, but now at an angle passing through this point. And it doesn't matter where the rays come from on the lens, even if they come towards the edges, they pass through the same point. This is the ideal lens. In the real world, this doesn't quite happen. As you go further towards the edges, the rays don't quite make it to the point, and we call this spherical aberration. By taking away all the nasty features of the real world and staying in the physics world, which is always pristine and no perturbations, we have a perfect lens. So lenses can concentrate light. Of course, when you hear about lenses, you would have heard the term focusing with a lens. So it focuses the light to the point. But that's not how we typically use lenses. We usually use them for imaging, and to understand how they could play both roles, we have to go into the inner workings of what the element itself is doing. And so I'm going to show you just one cartoon slide with real physics in it. This is the only slide with any serious physics. And it's physics that you know very, very well. It's just the concept of refraction. And the idea, formulated by Snell many, many years ago, is that if light, this arrow of light, this ray of light, travels from, say, air into water or the glass of the lens, when it hits the boundary between two substances, it doesn't matter what they are, but if it hits the boundary, it's going to change its angle. And the way it works is that if it goes into a medium that's more dense, so for example, going from air into water, it will bend inwards. So you see this ray would have gone straight like that, but now it bends towards this dotted line. So the trick here, the only physics you need to know to understand how lenses work, is that when light hits a boundary between any two substances, it will bend. It might bend towards the normal or away from the normal, but it's going to bend. And you can see this if you just put a pencil into a piece of into a glass of water and you have a look at it from the side, you'll see the bent pencil. It's because the rays of light that come to your eye are following this bent path. Okay, so lenses exploit this idea of refraction, and I want you to remember that refraction is just a fancy way of saying bending light. So what you want to do is you want to engineer this element that's going to bend the light to make it bend it in a particular way. Okay, let's see how we could play with the concept of a lens with this idea. And here's something that you can actually try when you get back to your room. So because the bending depends on the two substances, if you change what they are, of course it will change the way light bends. So previously when I showed you the lens, the rays coming in, it focused all the light to a point. It concentrated the light. But now what I've done in this little cartoon is I've taken the lens and I've imagined that I've placed inside a container that's more dense than the material of the lens. This would be like taking your plastic lens and putting it into a beaker of, say, oil. So what will happen now? Well, the medium of the lens is less dense than the medium around it. So rather than concentrating the light, it will diverge the light. And so what will happen is the front ray goes straight through as before, but the edge rays will not bend inwards, they will bend outwards. They do exactly the opposite. And so you see, you can turn a positive lens that focuses or concentrates light into a negative lens, not by changing its form, but just by changing the environment in which it finds itself. So here you see the first example of how we could play with the lens without actually changing any of the properties of the lens. And we're going to keep doing this throughout the talk until we get to a point where we've changed everything about the lens. Okay, now we understand how lenses work, so let's go to imaging. So here's a lovely image that I took from the web. And it's how we usually understand imaging, right? So we have some camera, some device that's looking at an object in the distance, and we see an image, as you see here on the digital camera, of the object in the distance. This is a very nice photograph because it has actually two images. It has an image taken of the camera and the object, as well as the image that the camera itself sees. And you see that this one is in focus and this one is out of focus. So we can't focus 2 points at different distances at the same time. So why is that? So let's go back to the lens and see how does it work as an imaging device rather than a concentrator of light. So not focusing the light, but imaging an object. Those are quite different concepts. If you want to burn an ant with your magnifying glass, I never did that. Or you want to image the moon or the stars, you have to make the lens work in a different way, even though it's precisely the same element. So what do you have to do differently? So what you have to do differently is you have to pick your distances very, very carefully. The distance from the object, which I'm just going to show with an arrow. You can replace the arrow by a candle or a picture of a person or a pretty landscape. But in physics, we just make an arrow to say it doesn't matter what the object is. What matters is the distance from the object to the lens and the distance from the lens to where you're going to try to find the image. So the image could be on your detector of your camera, or if you're holding a lens and you have a white piece of paper, you might be moving it back and forth to get a nice image on the wall of the thing in the distance. But these two distances, together with the focal length of the lens, a property of how close can it concentrate the light, these are the distances that matter. So how it works is that it's just as before. Imagine that the tip of the arrow, I'm going to follow the rays, these rays of light that could leave the tip. Well, one of them could go horizontal. It's going to hit the lens and bend downwards. So it's going to arrive at the tip of the other arrow. But it could also be that, there's a ray that goes straight down. And then it hits the middle of the lens, and it turns out that if your distances are exactly right, it will pass through, so it kind of gets bent on a straight line to arrive again at the same point as this ray. And then you can imagine that, well, what if it went at a steeper angle coming down? It hits the bottom of the lens, it will go straight and also arrive at the same point. It doesn't matter how you draw the angles here, the lens will always collect them at the same point, if those distances are carefully chosen. Only at those distances does this happen. And so you see that all the rays from the tip of this arrow arrive at the same place over there. This is what we mean by sharp focusing or sharp imaging. And if we were to move the distance, imagine I took this arrow and moved it a little bit to the left. Well, then you see that it would cross the rays at different places. It would be a blurry image. So your distances are very important, but the trick around imaging is just the bending of the lights. Nothing has changed in how the lens actually works. Of course, today, how many people still have good quality cameras? I'm just interested in a few. Yeah, when I give some talks to school children, and none of them own a camera. And then I ask them how many of them own a smartphone. And all of them do. And then I say to them, how many of you bought the smartphone to make telephone calls? And they all laugh. None of them make telephone calls with their smartphone. So what do they do with their smartphone? So they use it for imaging, right? They take selfies or Instagram. My daughter, I have a teenage daughter, she takes lots of Instagram photographs and posts them on all sorts of social media sites. So, and in fact, if you look at the billboards that sell these phones, what do they I've tried to upgrade my phone recently, and the question I asked the lady was, what is the battery life? And she told me that's irrelevant. Nobody cares about battery life anymore. I said, no, I care. She said, no, but we don't make phones for you anymore. It's true, because if you look at the billboard that tries to sell these phones, they show you a beautiful landscape, a mountain or a lake, and they say this photograph was taken with the iPhone 13, whatever the latest one is. And so actually a lot of engineering and money is going into the lenses that make up the camera system. This is actually an old phone, but my daughter wouldn't even consider using such a phone. But a lot of work's going into this. In fact, one of my friends works for Apple, and that's all he does. He designs the lenses to make the imaging system, because now you have to make the quality of the fancy cameras with large apertures and big lenses into a miniature system. And when I give talks to school children, I explain to them that the thickness of the phone is actually determined by the lenses and not the battery, not the electronics. So, but still, even though it looks different, the functionality is the same. It's using lenses in the same way to do the same thing. Okay, so if I come back to this, we can understand that if you get the distances right, as was the camera taking the photograph of this camera, has the distance right to get this a sharp image, but then the faraway field is not sharp. Whereas this one, of course, is sharp for the distance, but not for anything close. So this idea of being able to image only at specific distances is unavoidable. All right, all these lenses, of course, have been made of glass, but you can replace it and make it out of water. So actually, I have this with me. So if you'd like, I can pass it around. Let me take 1 second. I brought a few. So can you hear me while I unpack these? Great. So I'll talk while I do this. So Joshua Silver, this is actually his kind of creation, I suppose you would call it. And he believes that, well, he wants to solve the vision problem by having simple, robust solutions for people in the developing world. I'm going to pass this around. You have to be a little bit careful because it's filled with water. So this is a water lens. I'll send this one the other way. It's a little bit clumsy, right? And what you're going to find, well, if you look carefully at the picture, you'll also see it. There are two little syringes on the edges. And what you can do is put them on and adjust the syringes, which adjust the water pressure. I'm going to explain to you now in a second. Here's a modern version. You're lucky you get the modern version. Try not to over-pressurize it by turning too much. Turn outwards so it gets blurry and then bring it back into focus. Right, while it goes around, I'll explain it properly. So what did Joshua do? He decided that what the developing world needs is a tunable lens, so tunable glasses. How could you do that? Well, you can't do it with plastic or glass. So he has two thin membranes and he fills between them with water. And the water is in a syringe, which, as you will see when it passes around, can be controlled with two little dials. As you pump more water in, the membranes bend outwards, so you get a stronger lens. And as you undial it, it becomes flat again, so you get a thinner lens. And the idea is that you simply put them on, tune the two syringes until everything is in focus. It doesn't have to be the same for both eyes. And there you go, you have a pair of glasses. And if you happen to break them, no problem, you just have to find a tap.
With Joburg water.
So, fantastic idea. I absolutely love it. He runs this institute from Oxford, and his vision is he doesn't believe that you can really get optometrists out to remote areas. We're not training enough optometrists even for the developed world, forget about the developing world. And so his idea is let people solve their eye problems for themselves. And he's run a bunch of tests, and I'll show you a little graph. You can't really see the axes. I didn't want to make it too big, so I'll tell you what it's showing you. So on the horizontal axis is what the optometrist worked out the person really needed in terms of correction to their eyes. And then on the vertical axis is what the person with the water glasses found by themselves by just, dialing the syringes and saying, yeah, that looks about right. And what you can see is that all the data points sit more or less, there's a bit of a scatter, but more or less on a 45-degree line. That means that the average person with this water lens can make themselves a good pair of glasses as accurately as they would have got if they'd gone to an optometrist. Of course, he's not suggesting that you throw away your glasses and replace them with a syringe solution. It's horses for courses. Okay. So you can make a lens out of water if you engineer it very nicely.
So can I ask you a question? Does the quality of water matter?
It probably would. If the water's very dirty, you also have a dirty lens, right?
You could put wine in it.
You could put wine in it.
How about a little whiskey alcohol?
Okay, so great idea, very simple idea, but very impactful idea. I'll show you another example of a lens made of water. And in this case, it's very intriguing. So I was actually in Germany just a few months back, and in an institute that does microstructuring of materials. And in particular, they do it for X-rays. They make optics for X-rays. And it turns out that making optics for X-rays is very, very hard because the wavelength is very, very short. So I'm sure everybody in the room has had X-ray at some point in their life. We all have. And so you know how it works. You don't really see any optics, so to speak. It's more kind of points and shoots, and then you get kind of a picture at the back. But what this group are doing is they're making lenses for X-rays, but they're making them out of water. And the reason is that if you pass X-rays through a solid material, well, then it starts to damage the material. In the same way that you're encouraged not to have too many X-rays, right? And so what you see here, these little black kind of shaped out structures, they're actually hollow and they are nozzles. And what they're doing is they're pumping water through these nozzles. So here's one example of water coming through this one with all the others switched off. And you see that the water is following the shape of the nozzle. Now you have to do some careful engineering to make that happen. You have to pick your speeds of flow and your distances very, very carefully. But for a certain distance, the water shape will hold the nozzle shape. And it turns out that this nozzle shape is exactly what you need in the structure of the water, if you want to think about it like that, so that when the X-ray passes through it sees a lens. And of course, this is a lens in only one direction. If you shoot the water in this direction, then you get a lens in the opposite direction. So what they do is they shoot water in different directions, adjacently, and they pass the X-ray through it, and they can focus X-rays with water. So this is a beautiful idea because, you know, if the X-ray intensity gets too high, what do? You just switch off the water and then start again. Okay? So no permanent damage to the lens. So we can make water lenses for X-rays. There's another type of lens, maybe Andrew Chen, Robert mentioned that he spoke, and I saw his name on your list. Maybe he mentioned it, but you can make a lens out of gravity. Did he mention that? All right. So it's called gravitational lensing. It's quite an unbelievable idea that was put forward by Einstein, of course, a century ago, more than a century ago now. And the idea is a little bit abstract, but its visualization is very simple. The abstract part is that if you have matter, it tends to bend the space around it. And light, when it travels, follows a particular trajectory in space. Now, I told you that light travels in a straight line. That's not strictly true. It travels in a straight line if there's no matter around us. In this type of space, it's a straight line. But if you're in a space where there's large matter and you can bend the space around you, light takes the shortest path. That is the correct statement. And in this space, the shortest path is a straight line. But if there's a heavy object, the shortest path is not a straight line. And so what the light does, say from this star over here, the light would go out in different angles, lots of different rays, and we don't draw all of them. We typically draw a few to get the idea of what the light might do. So we draw the two extreme rays, and ordinarily it would just go straight and to the other end of the universe. And likewise, this arrow, if it was straight, would go all the way off over here. But no, they bend, and they bend around this heavy object. In this case, our galaxy, as it happens. And they focus together. So you see the arrows, the rays come back together, and now you've concentrated the light again, and you have a lens. But the lens is the galaxy itself. And so you can see objects that would otherwise be hidden by the galaxy by this gravitational lensing. This was predicted by Einstein and shown experimentally many, many times over, that it's a real phenomenon. So you can make very, very large lenses the sizes of galaxies, and use gravity instead of glass or plastic or water as the means to make the light bend. All right. So those are all examples of something bending the light so that they all arrive in the right place so that we have very nice imaging. Now I'm going to show you something that we do in my lab. I told you I would not talk about my research, but I couldn't help myself. So I'm going to show you something we do in my lab where we make a quantum camera. And in this particular imaging system, there are no lenses at all. So how does it work? How many people in the audience have heard of quantum entanglement? Oh,
Quantum chaos.
we need to have more talks here. Robert.
Quantum theory.
Quantum entanglement, you don't have to worry about the details. It's kind of as science fiction. If you watch a lot of fantasy and science fiction, you would have heard it a million times. But quantum entanglement is the spooky action at a distance that Einstein hated. The idea that things can be connected even though they may be opposite ends of the universe. If you do something to the one particle, you change something on the other. So what we do in my lab is we make this spooky action become real. We actually make entangled particles. The details are not important. I showed it just in this cartoon. We have a little optic where if we bring in some light, we get two particles of light going out, these two red blobs. And they are entangled. It means that if I send one red blob to that corner of the room and another one to this corner, if I change something there, this one immediately changes on the other side. So if I look at these two blobs coming out, it turns out that a property of the entanglement is that they are connected. And so the connection means that wherever you find one, you know where you're going to find the other. So let me show you that in a little cartoon. Each one arrives randomly over here inside my magnifying glass, and randomly this one in its magnifying glass. But if I know where this one is, I know for sure where that one is. That means that they're entangled. It's a property of nature. And I can use this for imaging. So what I can do is I take the two arms, the two red blobs. Think of arm A and arm B as being these two entangled particles. And one of them I'm going to send to this corner of the room. And I'm going to pass it through an object. And the object is going to be a little ghost. And the other particle I'm going to send over here to this end of the room. It's never going to see that object. It doesn't know there's an object there. It's got nothing to do with it. It's never been to that part of the room. It goes over here, and I'm going to send it to my camera. So you can think of it like this. Imagine I've got two torches. And the one torch I shine on the object, and the other torch I shine on my camera. And now I want to know, can I see an object on the camera? Well, of course, ordinarily we're saying no, because there's no connection between the object and the camera. But because they have this quantum connection, if I look on the camera, then this is what I see. The photons arrive randomly, but as they arrive, they are connected to one another. And so the camera photon over here sees what the other photon saw over there, even though it's never been there. And so now you see my little ghost appearing on the camera. So this is quantum imaging, and there are no lenses anywhere in the system. Nature gives us the connection. We don't need to man-make it with optical elements. So all the lenses that I've shown you up to now, except for the gravity one, have been man-made, engineered to bend the light in a particular way. And here there's no bending at all. All right. But now I am going to go back to the bending of light. And I'm finally coming to the topic, in case you're wondering if I'm ever going to get to the topic of lenses out of air. So here's I Googled air to try and find, could I have a nice slide for air? And this is the best I could get. So I'm going to have to make my own.
To read.
So when I was a student, I worked on this idea with my supervisor, Max Michaelis, and then when he retired and I became a researcher, he came back to my lab and continued to fiddle. And Max he unfortunately passed away a few years ago, but he is a very, very creative guy. So he was an English gentleman. He did science for fun. If you've ever been to UCT, the Michaelis Gallery of Arts, our National Gallery, that's the Michaelis family. So he comes from this family. And so he only did physics if it was going to be fun and exciting and crazy. Otherwise, what was the point? His view of science. And so the idea was, could we make a lens out of air? The answer, of course, is yes. So what equipment do we need to do this? So I like to give this talk sometimes when I speak to, when I go to some previously disadvantaged universities. Because I tell them, look, if you want to do some cool science, like I'm going to show you now, then the only equipment you need for this particular experiment is a piece of scrap metal pipe. That's all we're going to use. So equipment that we need, piece of scrap metal pipe. Any scrap metal pipe will do. What physics do we need? The physics that we need is just the mirage effect. Everybody, I'm sure, has heard or seen the mirage effect, yes?
No.
Otherwise, I'm going to tell you to go back to your university and get a refund. Okay, so the mirage effects, of course, you've seen it in some form or other, is when, for example, many manifestations, but I suppose in the popular literature it would be that you're in the desert and the sand gets very hot, there's a shimmering of the air because of the gradient in the temperature, and so you think there's water in the distance, but there's not. Probably a more realistic scenario is you're driving maybe through the Karoo and you're on a road, it's very hot, and so of course the road is hot and you see the shimmering effect. Why do you see this? So here's a nice little illustration. There's sky above the road, of course, here's some truck, but here you see the sky underneath on top of the road. Why is it that you can see the sky as if it's coming from the road? And it's because of this. Here is the road, and here is the air above it. And of course, the road is hot, and so the air directly above the road is also hot. And as you go farther away up from the road, going higher and higher, the air gets cooler. So near the road, the air is hot, and hot gases are less dense than, say, cool gases. And as you go higher, the air cools down, and cold gases, in general, are more dense than hot gases. So the density changes with the temperature, right? It's less dense here and it's more dense there. That means that for light, it looks like it's thicker over here and thinner over there. So what happens when a light ray comes into this system? Well, if it comes in, it wants to bend towards the more dense part because it thinks that you have different substances there, just like I showed you earlier with the water and the air. Except this time it's not two distinct substances, but like a graduation of substances. And so it bends, and it keeps bending towards the part that's cooler. And so the light ray comes in, say, from the sky, it bends, some of them hit the road, that's why you can still see the road. But you see the sky ray, in some instances, doesn't hit the road, and it bends upwards. So if you're standing over here, what do you see? Well, if you're looking down along this arrow, you have to follow the arrow backwards to see what you would observe. And so if you follow it backwards, you see the sky, but you think it's on a straight line because your brain tells you light travels on a straight line. And so your eye says, no, if I follow a straight line from this point, it's coming from here. And so I see the sky as if it's coming from there. So this is the mirage effect. And why do we need it to make a lens? Well, imagine I could take the road and curl it up to form a tube. So here's what I'm going to do. So here's my road, and here's the air, and I'm going to curl the road up to form a tube. And now you see that if I could keep the gradient of the temperature, and I'll come back to that in a second, then it would be hot around the edges and cool in the middle. And this is just kind of looking down the road, and so that means that it's a pipe, with a circular end, and this is a cross section of the pipe. And so I would have hot on the edges and cold in the middle. And so now if I pass my light through that, then the ray will bend towards the cooler parts. This ray will bend towards the cooler parts. And now I have a concentrator of light. So all I have to do is bend a road around itself. But of course, that's a little bit difficult, and so that's why we need the metal pipe. But you can see what's needed here. What's needed is to make the air next to the pipe edge very hot, and the air inside the middle of the pipe not as hot. Cool would be great, but not as hot is fine. And so that's what you do. You take your piece of metal pipe and you just heat it up by any means that you like. If you just did that, it wouldn't work particularly well. And the reason, of course, is that we would have convection currents. Okay, so if you've ever stood above your gas heater in your room, and put your above a fire, you can feel the air currents moving around. And so the temperature gradient that we want, which over here has got a lovely symmetry of cooler in the middle and hot on the edges, wouldn't be like that. It would be some other weird structure. So how can we make it do what we want? Well, it turns out that the answer is to spin the pipe. Okay, so I lied and I said we just need a piece of pipe. In fact, when I did this, the first time I went around looking for old second-hand sewing machines. You wouldn't believe how hard it is to find a sewing machine. But yeah, you're probably right. So you connect your pipe to an old sewing machine, you spin the pipe, it makes the temperature gradient symmetric, and this is what happens. You have a lens, and the lens focal length changes with the speed and, of course, the temperature that you have the pipe at. In much the same way that the water lens that's floating around somewhere here can be controlled by the pressure of the water. So you have some dials. Here the dials are more mechanical to change the focal length of the lens. But this is a very mechanical system with lots of moving parts. So when Max came back to my lab, he wanted to do it a little bit differently. I forgot to show you the slide. So when Max did this the first time, he actually spun the pipe really, really well, and you see he could image this water. If you've ever been to Durban, you'd know this tower, but maybe if you don't know Durban well, you wouldn't. But this tower is about 5 kilometers from the Howard College campus. And so you couldn't see it very well, usually, but through the gas lens, we call this a gas lens, he could image this water tower in the distance. And he played around with the moon and the sunspots and actually got into the cover of Nature. So whenever I go to these universities, they always say, what we need is more equipment. And I always say, no, what you need is better people. If you have great people, you can do things with just a straight piece of metal pipe and get onto the cover of Nature. So creativity is underappreciated, I think, in science. You make up for lack of creativity by lots of money. I don't believe in that. All right, so Max was very, very creative. So when he came back to my lab much later, he said, why don't we try this again, but this time not spin the pipe. And let's try to get the temperature gradients by getting flames to follow the path of the pipe, to spiral down the pipe. And the first thing he said to me when he came in, he said, I was at the CSR at the time, he said, do you happen to have a safety committee at the CSR? I said, yes, of course. He said, oh, that's a pity. So we did not tell them about this experiment. And this is a little cartoon of it, and I'm going to explain what it is in a moment. I'll come back to this beautiful picture at the end. I call this aero optics. So it's controlling light with air. So here's the idea. So you have a laser beam, and you pass it through the hot pipe that I mentioned earlier. And I told you that it would ideally focus the light. Well, actually, it focused the light around the edges very well, but not so well in the middle, because the gradient around the boundary is great, but not so much in the middle. And so you get quite a nice ring focus, but that's not a great lens. So then the idea was, okay, what if we took a flame, like from an oxyacetylene burner, and we got the flame by engineering the pipe to have a slightly different geometry to spiral as it traveled down the pipe. So what you have to imagine is you have a a student that you're prepared to sacrifice. And you give the student an oxyacetylene torch, and you've engineered this pipe so that at the right angle, the flame ought to spiral down the thing and come out the other side. And while it's spiraling it through, what you're going to do is you're going to shine the laser beam through at the same time, and the hope is that then it should focus the light. And in fact, if you combine them, then you get a great focus. So this is what it looks like in the lab. So this really is the oxyacetylene torch. Here's the pipe, and it's got a particular cusp here to guide the flame in so that it will spiral down this pipe. Of course, you burn quite a lot of pipes, and you go through quite a lot of students as well. But that's, as I like to tell the management of WITS, you know, our equipment's very sensitive, but students are coming every year. And you see actually the gradient of the temperature. You can actually visualize it now, and you can see that it's very hot around the edges. And I mean, even without measuring the temperature, I think you can agree that it looks like it's hot around the edges, and it looks like it's cooler in the middle, and it really is. I'll show you that we can really measure that and confirm it. And here you see a kind of a side-on picture of this flame coming in and spiraling and coming out on the other side. And so what we did is exactly this. So we combined this pipe idea with the spiraling flame. We call this a flame lens now. It's probably the most dangerous lens on the planet. And indeed, it does focus. Just to show you that we are serious scientists and not just doing crazy things with flames. We can, of course, model these systems. So we like to understand the physics of what's going on. And because we call it aero-optics, it means that you have to do aerodynamic modeling to understand the lens. Those are not phrases that you usually find together, aerodynamic modeling and lenses. So we had a collaboration actually with a group that normally model the wings and missiles of jet aircraft and how they flow through the air. And we said, yes, but now we need to model how light goes through a lens. And so these are some lovely simulations. The details are not really important, except that, you know, you can see the gradient again forming, and you can see the geometry in this kind of semi-transparent structure, the grayish structure. So this is a physical system where you can model very accurately, and you can measure and confirm that it works. And so I won't bore you with all the details, except to say the density that I mentioned that you need, it's shown here, going from low to high. And you see that the blue is the model. It's a computational fluid dynamics model. And the experiment is the red, and okay, there's a few deviations, but in fact, the agreement is very, very good. And this shape of the densities, in fact, the refractive index, but it's indicative of the density, is exactly what you need for it to act as a lens. And so you can do what we did before. You can do two things. You can first use it to image. So here you see some light-emitting diodes that are very, very blurry. And then we pass the same object through this flame lens, and you see that they come into focus. So we can image an object. And this rather ugly-looking thing at the bottom is a hole drilled in the material with a high-power laser beam passed through the lens. And so we can concentrate the light by using the lens as a focusing device. So imaging and focusing, but with nothing other than air. And you might be wondering at this point, why would you do such an experiment? Like, what would be the point? It's very similar in argument to the X-ray water case. But the X-ray water case actually is kind of 10 years after this. So I think they copied our ideas. If you have a look at this photograph, it's from the Rutherford Appleton laboratories. If you've ever been there, they're beautiful high-power laser laboratories outside Oxford. Actually quite far, so maybe 50 kilometers or so. And you see a person here, and so you can kind of make out that this element, which is actually a lens, is about the same size, or similar size to the person, right? So it's kind of meter scale lenses, very, very large. Why would they have such large lenses? The reason is that if you have a high power laser beam, no matter how much care you put into making this lens, it always absorbs a little bit of the light. And if you have enough power, that little bit turns out to be quite a lot. And so these lenses actually get damaged very, very easily. And even if they're not damaged, they get so hot that you have to wait for them to cool down. And so in these laboratories with these high power laser beams, they fire one pulse through the optical system, and then they wait several hours for it to cool down, and then they have another pulse. And so the idea was, could we make an indestructible lens that would never absorb anything, and if it got damaged, would immediately just self-heal itself? Because if it's made of air and you have a plasma, in microseconds the plasma's gone and your lens is recovered again. And so you could have a lens that would never get destroyed. And so that's the dream, and that's where we wanted to go. Of course, these are pristine lenses, whereas ours are a little bit clumsy, and people don't like using flames as solutions. But it does work, and so coming to the very end of the talk, I hope I've shown you a little bit about how lenses work, change your paradigm a little bit, that lenses don't have to be made out of glass, that you can make lenses out of many different systems with many different physics, including a little bit of crazy physics, and that indeed you can make lenses out of thin air. So on that note, I thank you very much for listening.
Thank you, Andrew. I think Adam Habib would be very reluctant to employ you if you knew that this at the National Laser Centre. Are there any questions that anyone would like to ask? Any comments or questions you would like to ask?
I would like to see inside the speaker's brain.
We would have loved my supervisor. Great talk.
Do you think those water glasses or lenses are likely to become commercially viable?
If you look at, did you get a hand on the modern version?
Yeah.
And that modern version is about 5 years old now.
Okay.
So if you go to Joshua Silver, you Google his name, and I think this has been recorded, right? So you can get his name at the top of the slide. If you go to Google, you'll find the latest version. They actually look pretty good.
Yeah, it's like using a pair of binoculars.
Exactly. And his idea, the modern version, is that you adjust the water pressure and then you disengage the syringe. And then when you find that your eyes are deteriorating, you just plug it back in and adjust it again. Now, he's really engineered it much, but these were kind of very clumsy old versions that he gave students. Go and have a look at his webpage. I don't think it would ever be suitable for this audience, but you can imagine that there is a market for this.
Sorry, look, I'm not a physicist or anything like that, and then you fired me the minute you saw me. But how much does dust in the air affect all this air lens?
That's a great question. So it does not affect the air lens at all, because if the dust were to vaporize, you get a little plasma, like a little spark in the air. The lens would break at that point, but because it's in air, it just immediately is back again as soon as that plasma is moved off. But in the physical lens, if you get a piece of dust on the glass or the mirror, when you get a little plasma, it leaves a mark on the lens. And that mark absorbs even more light, so it's a runaway effect. As soon as you get that little defect, you can throw away the lens. And these lenses cost millions and millions of euros.
Andrew, how do you explain to your granddaughter when she asks you, which way does the hot and the cold water move? Does the hot water move towards the cold, or does the cold move towards the hot? That's a 10-year-old, right?
I mean, I guess it's relative, right? But I mean, the physics theory would say hot moves to cold, but you can view it either way, I suppose. But in the case of the air, right? So in the case of the air, I mean, the convection current you can calculate. So you can see how the air would move in that fluid. And then the trick here is to break that problem, right? So you don't want mixing. You would like ideally to heat the air and keep it in a fixed layer by the rotation of the system. So you don't want any mixing. As soon as you get mixing, you have no lens.
So the guys at Appleton expressed any interest in your concepts?
I mean, I did it just for fun. Max was pretty adamant that this is really a solution that one should work on, and but there's it would take a lot of engineering. So no, that's too dangerous, and also the aberrations are too bad. It's not the world's best lens, and these guys, of course, spend billions and billions on their optics, so they want pristine beams, and it's very far from being practical.
Okay. If there are no further questions, I'll ask Alan to say a few words. Oh yes, we need your clock then. I need the master classes back, please. Thank you.
Okay, then we'll come back to it. One here. Two there. Well, Andrew, I must say, it was very interesting and very amusing, but most of all, your passion for the subject is incredible, I must say. And you must be an excellent teacher, if you can put it over like that. But then the more I looked at this use of the word laboratory, the more I thought about, I can only imagine it's a bit like a disco working in there. Lights flashing, looking through pipes. It must be very interesting, in fact. And then when you started using physics speak for, what was it, cartoons, well, then I imagined that in this laboratory, people were rolling around laughing. And actually, you were just talking about drawings of things. But I must say, it's been very interesting, and I'm sure I can speak for all of us. It's been a really entertaining evening, making something that's sort of so incredible to most of us, especially not physicists, more understandable. As a small gesture of our thank you, and I pass you this way.
Unfortunately, Andrew's wife couldn't join us this evening for dinner, but when he gave the virtual talk, he said, "Oh, thank you so much. I'll take my wife out for a nice dinner." I'm sure it was a very nice dinner. Thank you, Andrew. Thank you, everybody.
Thank you very much for listening.